Our story begins right here, in our own cosmic neighborhood. We live on a beautiful blue planet, a world teeming with life. This planet, Earth, is not alone. It travels through the vast, dark emptiness of space in the company of other worlds. Together, we are all part of a grand system, a family of planets, moons, asteroids, and comets. We call this system the solar system. It is our home, our island in an immense cosmic ocean. At the very center of this system, holding everything together with its immense gravity, is a star. That star is our sun. It gives us light. It gives us warmth. It is the engine that drives life on Earth. Every planet you can name, from fiery Mercury, closest to the sun, to the distant icy giants Neptune and Uranus, is a member of this family. Each one follows a path, an orbit, around our parent star. For thousands of years, we looked up at these wandering lights in the night sky. We told stories about them. We tried to understand their movements. We slowly, piece by piece, mapped out the local geography of space. We came to understand that Earth was not the center of everything. Instead, we were part of a much larger, more magnificent dance, choreographed by the immense power of the sun. This realization was just the beginning of our journey. We learned that our solar system is a place of incredible diversity and wonder. It contains worlds with crushing atmospheres, like Venus, and worlds that are little more than frozen deserts, like Mars. It has gas giants so large that all the other planets could fit inside them. It has rings of ice and dust that glitter like a celestial necklace around Saturn. It has moons that may hide vast oceans of liquid water beneath their frozen shells. All of this entire collection of worlds and wonders, exists within the powerful influence of our sun. Its light touches everything, but its influence extends far beyond what we can see with our eyes. This cosmic home of ours is not static. It is a dynamic, ever-changing place. Comets streak across the darkness, their tails of ice and dust marking their passage. Asteroids tumble through the void, ancient relics from the birth of the planets, and all the while the sun shines, pouring out a tremendous amount of energy into space. This energy travels outward in all directions, shaping the environment of every planet. It defines the boundaries of our home. To truly understand our place in the universe, we first had to understand the true reach of our sun and the nature of the space that lies just beyond its grasp. Our curiosity pushed us to look farther. The sun is more than just a giant ball of light and heat hanging in our sky. It is an active, churning, and incredibly powerful star. From its surface, it constantly releases a stream of charged particles. These particles, mostly electrons and protons, are flung outward into space at incredible speeds, traveling at over 1 million miles per hour. This constant outflow is called the solar wind. Think of it as the sun's breath, perpetually exhaling into the cosmos. This wind is invisible to our eyes, but it is a powerful force that travels far beyond the orbit of the most distant planet, Neptune. It fills the entire solar system. This solar wind is profoundly important for us here on Earth. Our planet has a magnetic field that acts like a shield, deflecting the most intense parts of this particle stream. When some of these particles do sneak through near the poles, they create the beautiful auroras, the northern and southern lights. But the solar wind's influence is much, much bigger than that. It carves out a vast region of space that is dominated by the sun's presence. Everything inside this region is bathed in the sun's particles and magnetic fields. This is the sun's sphere of influence, its kingdom in the vast emptiness of the galaxy. The solar wind does not travel forever. As it moves farther and farther from the sun, it begins to slow down. The push from the sun gets weaker with distance. Eventually, many billions of miles away from home, this solar wind encounters something else. It meets the environment of the galaxy itself. Out there in the space between the stars, there is a different kind of wind. This is the interstellar medium, made of particles and radiation from other stars, from ancient supernovas, and from the birth of the galaxy itself. The solar wind pushes outward, and the interstellar medium pushes inward. This cosmic struggle defines the true edge of our solar system. It is not marked by the last planet, but by the point where the sun's breath finally gives out. It is the place where the solar wind, after its long journey from the heart of our system, is no longer strong enough to push back against the vast ocean of interstellar space. For a long time, we could only imagine what this boundary might be like. We had theories and models, but we had never been there. To know for sure, we would have to send a messenger. We would have to go and see for ourselves. Imagine our entire solar system, with the sun, the planets, and everything else, enclosed within a gigantic bubble. This bubble is not made of soap and water, but of the sun's own solar wind. Scientists call this bubble the heliosphere. The helio part comes from the Greek word for the sun, so it is literally the sun's sphere. It is a vast protective cocoon that our sun creates around us as we journey through the Milky Way galaxy. Inside this bubble, we are in the sun's territory. The environment is dominated by particles and magnetic fields that came from our star. It is the domain of the sun. Outside of this bubble is a completely different realm. This is interstellar space. The word interstellar simply means between the stars. It is the great expanse that separates our solar system from the next star system, Proxima Centauri, which is over 4 light-years away. This space is not completely empty. It is filled with a thin soup of particles, a mixture of gas, dust, and plasma, known as the local interstellar medium. This medium has its own temperature, its own density, and its own magnetic field. It is the galactic environment, raw and unfiltered by our sun. The boundary of our heliosphere is where these two environments meet. This border is called the heliopause. Here, the outward pressure from our sun's solar wind finally comes into balance with the inward pressure of the interstellar medium. It is the ultimate frontier of the solar system. Crossing the heliopause means leaving the sun's protective bubble and entering the true beginning of interstellar space. For decades, the heliopause was a theoretical concept. Scientists knew it must exist, but they had no way of knowing exactly what it was like. Was it a smooth, calm boundary, or was it a turbulent, chaotic place? Understanding this boundary is crucial. The heliosphere acts as a shield, protecting the planets, including Earth, from a significant amount of high-energy galactic cosmic rays. These are particles accelerated to nearly the speed of light by distant cosmic events like exploding stars. Our heliosphere deflects many of them, making our solar system a safer place for life to exist. Learning about the nature of this shield, its strength and its structure, is not just an academic question. It is about understanding the very conditions that allow for our existence. To do that, we had to send explorers to the edge. In the summer of 1977, humanity launched 2 extraordinary envoys to the cosmos. They were twin spacecraft named Voyager 1 and Voyager 2. Their original mission was ambitious, a grand tour of the outer solar system. They were designed to take advantage of a rare alignment of the giant planets, Jupiter, Saturn, Uranus, and Neptune, that happens only once every 176 years. Using a clever technique called a gravity assist, they would fly by one planet and use its gravity to be flung onward to the next, like a cosmic slingshot. This would allow them to visit multiple worlds in a single, continuous journey. These probes were marvels of engineering for their time, built to endure a long and difficult voyage. They were equipped with a suite of scientific instruments to study planets, moons, magnetic fields, and particles. They also carried a message for any civilization that might one day find them. This message was the Golden Record, a gold-plated phonograph record containing sounds and images selected to portray the diversity of life and culture on Earth. It was a greeting, a time capsule, a bottle thrown into the cosmic ocean. The probes were built to last, but their primary mission was expected to be over in about 5 years after the planetary encounters. But an amazing thing happened. The Voyagers just kept going. After they completed their breathtaking tours of the giant planets, sending back images and data that revolutionized our understanding of the outer solar system, their mission was far from over. Their instruments were still working, their plutonium power sources were still providing electricity, and they were still traveling, heading inexorably outward, away from the sun and toward the unknown frontier of interstellar space. Their mission was extended. They became our first interstellar explorers. For decades, they flew through the dark, cold outer reaches of the heliosphere. Year after year, they faithfully radioed back data about their journey. They traveled farther from home than any human-made object had ever gone before. The light from our sun grew fainter and fainter, eventually becoming just another bright star in their view. They were sailing into uncharted territory, heading for a boundary that no one had ever crossed. They were our eyes and ears at the very edge of the solar system, poised to answer a question that had lingered for generations. What happens when our sun's influence finally ends? The journey of the Voyager probes is, honestly, a testament to endurance. For decades after their launch in 1977, they sailed through the vast, dark expanse of the outer solar system. They traveled billions upon billions of miles, moving farther from Earth every single second. The signals they sent back, traveling at the speed of light, took hours to reach us. The team of scientists and engineers on the ground had to be incredibly patient, listening to the faint whispers from these distant explorers. The Voyagers were venturing into a region called the Heliosheath, the outermost layer of our heliosphere, where the solar wind begins to slow down and become more turbulent as it approaches the interstellar boundary. As the years turned into decades, the Voyagers continued their lonely voyage. Their power supplies, fueled by the radioactive decay of plutonium, slowly diminished. To conserve energy, engineers on Earth had to make difficult choices, turning off certain instruments one by one. But the crucial instruments for detecting particles and magnetic fields were kept running. These were the senses that would tell us when the Great Crossing had occurred. The mission was no longer about visiting planets. It was now about a single monumental goal: to punch through the bubble of the heliosphere and enter the space between the stars. The scientists watched the data closely. They were looking for specific signs that would signal the crossing of the heliopause. They expected the number of particles from our sun to drop dramatically. At the same time, they expected the number of high-energy galactic cosmic rays, particles from outside our solar system, to spike. These two changes, happening together, would be the definitive proof. It would be like stepping out of a house into the rain. You would no longer feel the air from the air conditioner, but you would suddenly feel the raindrops from the outside world. This waiting game was filled with anticipation and uncertainty. No one knew exactly how thick the boundary region was, or what its precise characteristics would be. The Voyagers were flying into the complete unknown. They were mapping a territory that had only ever been imagined in computer models and scientific theories. Every packet of data they sent back was a new piece of a puzzle that had never been seen before. The probes, designed for a 5-year mission, were now approaching half a century of operation, becoming humanity's longest-serving and most distant explorers. Their greatest discovery was still ahead of them. The moment finally came on August 25th, 2012. After a journey of 35 years and more than 11 billion miles, Voyager 1 experienced a sudden and dramatic change in its environment. The instruments on board detected a sharp drop in the number of solar wind particles. It was as if the sun's breath had suddenly vanished. At the very same time, the probe was hit by a surge of galactic cosmic rays, the particles from interstellar space. The data was clear and undeniable. Voyager 1 had crossed the heliopause. It had left the solar system and was now flying through the space between the stars. Humanity had officially become an interstellar species. This was a monumental achievement in the history of exploration. For the first time, a human-made object had exited the protective cocoon of our sun and entered the galactic medium. It was a moment comparable to the first explorers crossing an ocean or the first astronauts setting foot on the moon. We were now directly sampling the material of the galaxy. All our previous knowledge of this region was indirect, based on observations of light and particles that made their way into our solar system. Now, We were there. We were tasting the cosmic ocean itself. Then, 6 years later, it happened again. In November 2018, on a different trajectory and billions of miles away from its twin, Voyager 2 also crossed the heliopause. Its instruments recorded the same dramatic shift. The solar wind disappeared, and the galactic cosmic rays flooded in. This second crossing was incredibly important. It confirmed that the discovery made by Voyager 1 was not a fluke or a localized anomaly. The heliopause was a real large-scale boundary surrounding our entire solar system. It also showed that the boundary is not a perfect sphere. Voyager 2 crossed at a different distance from the Sun than Voyager 1 did, proving the heliosphere is dynamic, breathing in and out. The twin probes, now true interstellar travelers, continued to send back priceless information. They were our first-hand witnesses to the environment outside our home. And what they found was not what anyone had expected. The data they returned challenged our theories and painted a surprising picture of the solar system's edge. They had passed through the final frontier, but their journey of discovery was only just beginning. The most startling revelation was yet to come, a finding that would force us to rethink the very nature of this cosmic boundary. As the Voyager probes analyzed the plasma just outside the heliopause, they sent back a reading that left scientists stunned. The temperature of this region was incredibly high. It was not just warm, it was scorching. The data indicated temperatures between 30,000 and 50,000 degrees Kelvin. That's up to an astonishing 90,000 degrees Fahrenheit. This was completely unexpected. Our models had predicted a much cooler boundary. It was as if our solar system was encased in a wall of fire, a superheated shell of plasma at the very edge of the sun's influence. The discovery was mind-boggling. This extreme heat was found in the region just beyond the heliopause, in the interstellar medium that is being compressed and heated by the outward-moving heliosphere. Think of it like the bow wave in front of a boat moving through water. The boat is our heliosphere journeying through the galaxy. The water it pushes aside is the interstellar medium. This process of pushing and compressing the interstellar plasma heats it up to these incredible temperatures. It is 10 times hotter than scientists had predicted, a discovery that sent astrophysicists back to their drawing boards to revise their models of how stars interact with their galactic surroundings. The data from both Voyager 1 and Voyager 2 confirmed this high-temperature zone. Since they crossed the boundary at different locations and different times, it proved that this wall of fire is a persistent feature of our solar system's edge. It is a fundamental characteristic of the interaction between our sun's domain and the galaxy at large. This finding is not just a curiosity. It fundamentally changes our understanding of the physics at play. It tells us that the boundary is a much more complex and energetic place than we ever imagined. The sun's interaction with the galaxy creates a far more dramatic frontier. One of the big surprises was related to the magnetic fields. Scientists expected that the sun's magnetic field, carried outward by the solar wind, would be oriented differently from the magnetic field of the local interstellar medium. But both Voyager 1 and, later, Voyager 2 found something strange. The magnetic field just outside the heliopause was almost perfectly parallel to the magnetic field just inside it. It was as if the two fields had somehow aligned themselves across this boundary. This was a major puzzle that scientists are still working to solve. It suggests a more intimate and mysterious connection between our solar system and the galaxy than we ever knew. When people hear about a wall of fire at 90,000 degrees Fahrenheit, the first question is always the same. How did the Voyager probe survive? Why didn't they melt or burn up instantly? The answer lies in a crucial and often misunderstood difference between two concepts: temperature and heat. In our everyday lives on Earth, we use these words almost interchangeably. If a stove is at a high temperature, it feels hot and can burn you. But in the near-perfect vacuum of space, this relationship breaks down completely. It is a paradox that saved our intrepid explorers. Temperature is a measure of how fast particles are moving. A high temperature means the individual atoms and ions in the plasma are zipping around at incredible speeds. In this sense, the region at the edge of our solar system is indeed extremely hot. The particles there are incredibly energetic, moving with the kind of speed you would find in the outer layers of a star. If you could measure the speed of a single particle, you would get a very high temperature reading. The Voyager's instruments did exactly that, and the readings were accurate. The plasma is indeed at a sizzling temperature. Heat, on the other hand, is about the transfer of energy. For you to feel hot, those fast-moving particles have to actually hit you and transfer their energy to you. This is where density comes into play. On Earth, the air around us is dense, meaning there are countless particles in every cubic inch. If the air is hot, trillions of particles bombard your skin every second, transferring a lot of energy and making you feel the heat. But the wall of fire at the edge of the solar system is an almost perfect vacuum. The density of particles is incredibly low, so even though the few particles that are there are moving very, very fast, high temperature, there are simply not enough of them to transfer any significant amount of energy to the spacecraft. A Voyager probe might be hit by one of these energetic particles only every now and then. The total amount of energy transferred is negligible. The spacecraft radiates its own internal heat into the cold of space much faster than it absorbs energy from this superheated low-density plasma. That is the secret to its survival. It is like being in an oven where there is only one molecule of hot air. You would not feel a thing. The discoveries made by the Voyager probes have fundamentally reshaped our map of the solar system. They have transformed the edge of our home from a theoretical concept into a real, tangible place. We now know that our solar system is wrapped in a superheated bubble, a wall of fire, that marks the boundary with the galaxy. We know that the magnetic fields at this boundary behave in unexpected ways. These are not just minor details. They are foundational truths about our place in the cosmos. The textbooks are literally being rewritten because of the data these 50-year-old probes continue to send home. This exploration of boundaries is at the very heart of science and human curiosity. We are a species that looks to the horizon and wonders what lies beyond. We climb mountains, we cross oceans, and we send spacecraft to the edge of the sun's influence for the same reason: to know. Each time we push into a new frontier, we learn something not just about the place we are exploring, but about ourselves and the context of our own existence. The Voyager mission has shown us the true scale of our solar neighborhood and the nature of the galactic sea in which our island floats. The journey is not over. The Voyagers continue to fly deeper into interstellar space, still reporting back on the conditions they encounter. They are our silent sentinels in the great dark, teaching us about the galaxy in a way we never could from within our heliosphere. They are a testament to the power of human ingenuity, curiosity, and the relentless desire to explore. They were built for a 5-year mission to see the planets, but they became our first messengers to the stars, a mission that will continue until their power finally fades, and they drift silently onward, carrying their golden record through the Milky Way. What the Voyagers have taught us is that the universe is always more strange, more complex, and more wonderful than we can imagine. Every time we think we have a complete picture, a new discovery comes along that adds unimagined detail and depth. Exploring boundaries, whether it is the edge of an ocean or the edge of a solar system, is how we grow. It is how we build a more complete understanding of the cosmos and our place within it. The fiery wall at the edge of our world is not an ending. It is a new beginning in our quest to understand everything.